Hello, my name's Anton. I am a programmer, and I'm going to talk about building a quick and dirty DSL. And before I start, I want to do a quick survey just to know what the audience is like. Not that I can change my talk or anything, but how many people have used regular expressions? Okay, and how many people know how a compiler works? And how many people have built their own compilers before? Okay.
I built one, but I don't know how it works.
Okay, so this is pretty good.
We have a result. We gave the Dragon book in their homes.
Which book?
Dragon book.
Don't know the Dragon book.
Yes. You're talking about compilers. Played years ago.
Okay, so
I have a copy of KNR.
I'm just going to go.
Ernie and Richie.
Yes.
Okay. I work on a product called Condatte, and basically to strip it down for just the context of the talk, it's a meal planning app, and it has other meal-related things like shopping list, inventory list, your recipe collection. And we're specifically going to talk about this part, which is recipe search. So when we were just sort of starting to build the product, we needed at least some rudimentary recipe search functionality. So what we did is we used Lucene, which is an open-sourced full-text search engine. And it's good for searching in just regular sort of documents. And we needed to make some adjustments, like modify the scoring function to sort of fit the specific case of searching for recipes, and had to implement rudimentary synonym handling. So when you're searching for, like basically, in Japanese, there are multiple ways to write the same thing. So we kind of handled that, and it's sort of okay-ish, mediocre quality limping along, and we were switched to working on other stuff. And as the other stuff got better, we wanted to now increase the quality of recipe searching. So the things that we wanted to do is being able to include and exclude ingredients in a more sort of data-like fashion as opposed to just full-text fashion. Food genre, style, preferences, we wanted to be able to include that. Handle allergies, and just simply have sort of better quality matches to what the person is searching. And as we were sort of thinking about this problem, there was one key observation, and the key observation is that there are only so many ingredients out there. So the idea was that it's basically the ingredient universe as a function of the number of recipes you've indexed will behave in a logarithmic kind of fashion. So for the first 1,000 recipes, you'll index maybe 1,000 ingredients, and for the next 1,000, you'll add maybe only 100, and then for the next 1,000, you'll add like 10 or something. So that would allow us to basically do a bunch of manual work up front in sort of building out the database. And once we've sort of conquered the steep part of the curve, adding more recipes to the index will be operationally light. And the nice part, of course, would be that we'd be able to do it in a sort of fully semantic manner. So you'd have an ingredient entity with the name and an ID, and you have the recipe that has ingredients text as the text thing. And when you're adding it to the index, you're basically building this sort of, the classic database relation thingy. Of course, it's not as simple because there are multiple ways of writing the same thing. So for this like ingredient scraping thing, you would also need you would only want one entry for the various ways of writing pork belly. So you need some kind of raw name to canonical name mapping thing happening. So we built this, and this is what the sort of operations screen looks like. So once you've added some more recipes, the unknown ingredients come up here as a sort of an ingredient request. And given any of these, what you can do is you can either ignore it, if it's, for example, some text string that is not an ingredient. People put all kinds of stuff in there. Or you can create it if you think it's an ingredient that hasn't been registered yet. Or you can map it to an existing ingredient if you think it's a sort of different way to write something that you have already registered. So here, you can sort of search what ingredients you have registered, and you can see sort of for every entry, there are multiple raw mappings, and this is like the canonical one. So it was one of those situations where you have to go a certain way and build out the system to a certain level until you can really tell if it's going to work or not. And you can probably imagine it doesn't quite work. So there's a problem. The problem is, this is torigara supu no moto, the powdered chicken stock thing. And, I could imagine there's probably, 5 ways or something to write this. But as I kept adding more recipes to the index, more and more and more and more and more ways of writing the same thing kept emerging. And it became pretty obvious that this logarithmic thing is the universe of ingredients is indeed probably like that. The universe of ways of writing them in Japanese is sort of a different curve, which goes from sort of operationally possible to operationally completely infeasible. So I basically underestimated the complexity of Japanese and the flexibility. Not only do you have katakana, kanji, and hiragana, you can also rearrange stuff fairly freely and it still makes complete sense. The underlying sort of problem here was that the expressive power of the system that I built did not match the level of complexity of the problem. And usually sort of when you run into this kind of thing, hacks just stop working. Like you cannot make a little hack and make everything sort of fit together. It's just like fundamentally broken. So you need another layer. That's how you fix these things usually, right? All problems in computer science can be solved by adding another layer of indirection. This is by this famous computer scientist. Except for the problem of having too many layers of indirection. So what we'd like to have here is an inverse regex kind of thing. So regular expressions are sort of their short syntax for matching a variety of strings. And we kind of want the inverse. We want a short syntax for generating a lot of raw mappings. So given something like this, where sort of the stuff in brackets is alternation, we kind of want to generate these 4, 2 times 2, 4 patterns, right? Except the actual thing for torigara supu no moto is a little longer. There's sort of some more stuff happening. So once you generate them, it's a lot. And it's actually even more complicated than that because you can have the sort of various modifiers in brackets or without brackets, prefixed or suffixed. So as you probably guessed, you want another level of indirection here. You basically want to pull out some stuff into variables, well, constants really, and then start composing them in a compact sort of manner. And once you do that, you can sort of nicely generate long lists of stuff that you want. Sorry.
Do you cover most use cases when you reach that level?
So I only built this morning. So I didn't get to plumb it all the way and see how much it covers. I got very excited and thought, finally I have something that I can distill, pull out of the context and still have a presentable thing that's like packageable into 20 minutes. Let's implement that. So I had the idea just last night, so I implemented it this morning and early afternoon. It's a 2-pass thing, so for that sort of little language, you need to parse it and construct a parse tree, and then you need to evaluate the parse tree to actually construct the list of strings. So how many lines do you guys think is going to be? Writing in Scala. Throw out a number at me. To build the parser and the evaluator for that language that I showed. Sorry, one sec. So basically not good at that. Yeah, so basically the program that will take this text and run this to produce this list. So I basically wrote a little DSL to produce various combinations of text.
Question. What's
Yeah.
DSL?
Oh, sorry, it's domain-specific language.
Can you explain what it means?
What are domain-specific languages? Yes. So normal programming languages like Java or JavaScript or whatever, they're called general purpose because you can basically do any kind of computation-related task. But the price you pay for this generality and flexibility is that the code becomes quite verbose. And on the flip side, you have very purpose-specific languages that allow you to express fairly difficult ideas fairly compactly, but they're limited in what you can do. So the classic example of a domain-specific language is SQL. So it's very good at querying data. And if you were to write it in a general language, it would be like a lot of loops and filtering and all kinds of stuff. So sort of a simple 3-line select would probably be 100 lines of Java or something like that. So that's what a domain-specific language is. So here we're basically trying to write a domain-specific language to generate sort of these strings. Okay. 300.
What
Scala.
What Scala?
Yeah.
20 lines?
20.
You can write everything in one language, in one line if you try to.
Fair point.
100.
100? So 110 lines is what I ended up with. This was focusing on readability more than the number of lines. This is kind of what it looks like. We'll look at it in a little bit of detail. So first, the parse tree structure. So we want to take this thing and make a parse tree out of it. This sort of thing. So the whole thing is a line, and it consists of concatenation of sort of the first guy with the rest of the stuff. So you have concatenation of a value, that is tori, and concatenation of the rest, which is an alternation, so the first pair of purple brackets of these two, and it is basically a tree structure, sort of a classic thing that you would get when parsing like an arithmetic expression or any code, really. And the case classes. So case classes in Scala are basically like structs in C. They're just a simple sort of blob with some fields in it kind of thing. So the case classes for this are, so you have line and expression, and expressions are concatenation, value, substitution, alternation. So substitution is when inside the line you use $ something. Alternation is when it's a purple brackets with two things. Concatenation is when two things are adjacent to each other. And then there's binding, which is when you have a symbol bound to an expression, which you can later reference through a substitution. So this is sort of the structure that we're going to aim for. And basically, first what we need to do is somehow parse the text to become this structure, and then we need to evaluate the structure to actually generate all the potential combinations of strings. How long have I known Japanese? I started studying it in university like 10 years ago, and I've lived here for 8. Yeah. So.
Academically, can you describe things in Japanese in the context of English of general known Chomsky stuff?
Sorry, I did not parse half of that.
Do you
Can I talk about this stuff in Japanese? Is what you're asking? No.
Can you describe the structure of the language of Japanese to the terminology that Noam Chomsky uses?
I don't really know what terminology he uses, but I can.
I'm curious because I'm trying to get a level of understanding and to see how long it would take for me to invest in Japanese. Sorry.
In order to build this sort of stuff.
I'm kind of weaving this off into left field right now, so I'm going to stop.
Okay, we can talk about this afterwards. Yeah, let's do that. So BNF grammar, it's like Bacchus-Naur form. It's a syntax for describing grammars for languages, which is typically used. So this is a reminder of what we're trying to write a grammar for, and this is what the grammar ends up looking like. So if you read it, it's basically so lines are a line followed by more lines, or just a line kind of thing, right? So symbol is a bunch of alphabetic characters. Or so a leaf node would be a bunch of textual characters like gara or something like that, or this like $ syntax with a symbol like you have here. So basically, this is the description of all the pieces that are needed to sort of build this thing. Who has seen context-free grammar definitions before? Okay, yeah. So this is basically what I wrote this after I wrote the actual code. But if you were more sort of strict with yourself, this is what you would sketch on paper before actually implementing stuff. Okay, so this is what we're going to implement, and how we're going to implement it. Of course, there's a DSL for building DSLs. It actually, you don't even need to like get an extra jar or anything. This isn't Scala util. It's just fantastic. So the implementation, this is what it looks like, and it actually looks very similar to the BNF grammar that we just looked at. So here's an example. So here we had lines being a line followed by more lines or a line, and here we have exactly that. So lines are a line followed by a new line character and more lines, or a line. And sort of likewise, you can see that a symbol is just like that regular expression, and that's what it is like here. And the same thing with the leaf node that I described. It's like either this like $, squiggly braces symbol, or it's the regular expression looks a little uglier because I have to escape a lot of stuff, but basically the same thing. And you can see that there's these like double caret symbols. So the left side is matching the text, and the right side is actually constructing those structs that I showed you in the previous slide. So simply, so for the leaf thing, for example, when we have a symbol between the dollar parentheses thing, it becomes a substitution with symbol. So value becomes just a value with the value passed in. Similarly, like alternation, basically the right side makes the objects out of the text that was matched.
Yeah, you treated space for readability. It's very unreadable.
It's a DSL, right? So you need to first learn to use the DSL before you can do it. This is not a general purpose language. It was also sort of unreadable to me. I've done this exercise once before, and it became throwaway code, but that's why the start time was pretty quick this time around. But yes. But it looks sort of surprisingly similar to the grammar. And the grammar is supposed to be sort of the ideal distilled form, right? So a pretty high level of expressivity. So now let's look at the top level evaluate function. So the idea is it's going to take the list of parsed lines, so the parse tree basically, and produce the list of generated strings. So that's what the type signature says, right? So it takes a sequence of line objects and produces a sequence of string. So first thing is we're going to do this iteratively, well, recursively, but almost the same thing in this case. And as we're evaluating, we're going to keep some state. And what that state is, well, from going from the bottom, the output that we've generated so far, the remaining lines that we still have to evaluate, and the symbol table, which is basically the table of mappings of symbols to the values that we get by evaluating the expressions that they're bound to. And then the call is going to be evaluate rec for recursive. So we're going to start with an empty symbol table with all the lines that were passed in for evaluation, and the output, it starts out with nothing, so an empty sequence. And this is the body of the recursive evaluator. And we're going to match on states. So this is a match case thing. Who has programmed these? They're not that popular yet in sort of general languages. But basically, they allow you to... it's a short way of writing sort of if my object has this kind of structure, then. It's a very, very short and condensed if then else kind of thing. Oh, sorry.
Like a switch?
Kind of like a switch, yes. So the first case, if so underscore means ignore. So we don't care what the symbol table is. If the remaining lines is an empty sequence, then we just output the output. So basically, we've examined and evaluated all the lines. So just return the output. And then the second one is, if it's not the first one, then we break apart the remaining lines into the top line and the new remaining lines. And we match on the line. So depending on what the line is, we do different stuff. And I didn't. Oh, interesting. Okay, never mind. The first case is when it's a binding. So when it's the val something equals the expression. So the binding, so this is once again, we're breaking apart the binding structure. So symbol and expression. And what we do is we call evaluate recursively with the new state. And what is the new state? since it's a binding, the output doesn't change. We haven't added any new output. Remaining lines is the remaining lines from here. And symbol table is the one that's get updated because we're processing a new binding. And how it is updated is by setting the symbol to evaluation of the expression with the current symbol table.
What's the symbol table?
A symbol table, so you know how we had a bunch of vals? So a symbol table is basically a map from the name of the val to the expression that it was bound to. So basically, this case, all it does is add a new entry into the symbol table. And then the second case is when it's an expression. So these are the ones that actually generate the output. So once again, we call evaluate recursively with the remaining lines. The symbol table hasn't changed. The only thing that has changed is the output. And how has it changed? We add to the existing output the evaluation of that expression with the current symbol table. Did they do a horrible job explaining this? So that's the evaluator. And the one thing that we have left to look at is the evaluate method for individual expressions. So the expression evaluate method, it takes the parsed expression and the symbol table and produces a list of generated strings. And it's very straightforward. So once again, it's a match on the expression. And if the expression is a straight up value, we just return a sequence of one element, that value. Yes, sir. Oh, 5 minutes, okay. If the expression is a substitution of a symbol, then we just look into the symbol table and look up that item, and that's what we return. No error checking. Concatenation is fairly simple, so evaluate the first expression through the symbol table and the second expression through the symbol table, and do cross product on them. So if you had 3 spellings of chicken and 3 spellings of soup, you will get 3 times 3, 9 combinations. And alternation, it basically evaluates all the possible choices in those purple brackets with the symbol table and then just flattens that list together. So the one remaining sort of interesting bit here is the cross product on sequences. So you can probably imagine that in the default library for the language, there is no such thing as an operator for cross product on sequences. But in Scala, you can basically define custom operations on data types. So you create this like implicit class thing. I'm not going to go into the details, but basically it takes a sequence and sort of decorates it with a new operator, and the new operator takes another sequence and basically does so this notation is basically a pair of a nested for loop, a for loop in a for loop, which produces you sort of all the 9 combinations if you have 3 and 3. So that's also kind of DSL-ish, and that's kind of why the IDE highlights it. It tells you that there's some like shady stuff going on. That's basically it. And it generates that huge list. So I wanted to finish with a couple quotes. I watched a video by, how do you pronounce that guy's name? Alan Kay? Alan Kay? Watched a video by him a couple days ago, and something that sort of stuck in my head is, he said that you can't really be doing new stuff with existing tools. To do something that's orders of magnitude ahead of current best, you need to build both the thing and the tools to build the thing. And as I was sort of preparing the slides and putting this quote on, it reminded me of a quote also paraphrased from Elon Musk, where he said, at a certain point, the innovation stops being about the thing, like the car, and it becomes about the thing that builds the thing, so the factory. So anyway, I thought that was kind of cool, and it's nice to every now and then have a little chance to practice what these guys preach. Yeah. Yeah. And sorry, the compulsory join us pitch. We are looking for rockstar engineers. We have a spacious, sunny office. We're focused on meaningful work and don't have any bureaucracy. And compensation is from Yeonjumang and an equity package. And What else? Oh yeah, we ship fairly regularly, so twice a week. So if you know anybody or know anybody who knows anybody who may be interested or who we should actively headhunt, please tell me. Thank you for your time.
Thank you very much.